Welcome to week 4. You survived exam number 1. That's great. Now we move on to whatever is next, which will probably be exam number 2. So we're going to talk, this week we're going to talk about confirmations. So we're going to go back to Newman projections and extend it to cyclic systems, which is going to be awesome because we're going to discover the world's perfect organic molecule. So we're going to get to cyclic systems. We're going to look at 6-membered rings in particular because they're awesome. And then we're going to also talk a little bit more about stereochemistry. So last week's lectures, we defined enantiomers, diastereomers, and that kind of stuff. This week, we're going to kind of learn how do we name them, how do we tell when they're different from each other, and we're going to learn a couple of exceptions to those rules, of course, as well. So the first few lectures this week are going to focus on conformational isomer stuff. So let's jump right in. So we're going to do cyclic confirmation. So we're going to look at what happens if we apply the idea of Newman projections and steric repulsion and gauche interactions and those kinds of things. What if we apply that idea, and eclipsed conformations, I guess, are going to come up as well. If we apply those ideas to carbon structures that are ring-shaped as opposed to just chains. Right? So the important takeaway from previous lectures has been that in general, we want to put our large groups opposite each other. We want them to be 180 degrees from each other when we draw them in a Newman projection, right? And you just had an exam on this, so this should all be fresh in your head. When we go to, so let's, right, if we have a, whatever, your standard Newman projection looks like this, right? And we have our large group. Let's put our large group, we'll put methyl group, a chlorine, and a hydrogen, right? So of those, the methyl group is the largest group because it has the most sigma bonds. And so on the back, we would put our large group over here to be opposite each other, hydrogen, and then let's make this an ethyl group. Right? The point being large group, they're 180 degrees from each other. This is the best. And if we had drawn one where they weren't 180 degrees from each other, what we would do is we would just rotate one of the atoms until we moved them into this anti-relationship. Anti, 180 degrees is most stable. Right? And so this is kind of our idea going forward is we want to do that. What happens when we look at cyclic compounds is the problem. Cyclic compounds can't rotate in the same way. Right? And so we're going to end up, when we draw our Newman projections for some cyclic compounds, we're going to end up with some examples where the two large groups kind of can't get out of each other's way. So let's start with cyclopropane. Okay, so this is cyclopropane. That's not how you spell cyclopropane. There we go, cyclopropane. So cyclopropane has 3 carbons in it, right? And those 3 carbons are all connected to each other because it's a 3-membered ring, etc., etc. So let's make this carbon A and this one carbon B. Let's draw a Newman projection where carbon A is in front. Right? Carbon A has got 2 hydrogens on it. And I guess we'll call this one carbon C. This is going to be carbon C over here. Right? And then carbon B is going to be behind. But notice that carbon B is attached to 2 hydrogens and carbon C, just like carbon A is. And so if carbon B is attached to carbon C, it kind of has to be in the same plane as carbon C because geometrically 3 points define a plane. And so that means that these other hydrogens are going to also end up in this eclipsed conformation, right? So because both A and B are connected to the same group over here, that forces everything into, this is forced into an eclipsed conformation. And we know that eclipsed conformations are bad. Eclipsed conformations have a lot of steric repulsion because you have a lot of groups with electrons that are all right next to each other, that are interacting with each other, that are repelling each other. Right? So eclipsed conformation is bad. Lots of steric repulsion. But wait, it gets worse, right? The other thing that we have is we have in a triangle, an equilateral triangle, because these are all carbon-carbon bonds, we have an internal angle of 60 degrees, right? That's just a property of triangles. But what that means is that a normal sp3 carbon wants to have, so let's do normal sp3 carbon, right? Our normal sp3 carbon, we have all four groups and they all kind of arrange themselves so that they're as far away from each other as possible, right? That's what steric repulsion does. It pushes those bonds as far away from each other as possible. And so in a normal sp3 carbon, we have a bond angle of about 109.5 degrees. That's what makes this sp3 carbon tetrahedral. And what we're saying when we say that an sp3 carbon is tetrahedral, what we're saying is that that is the bond angle or the angle between the bonds that gives us the least steric repulsion, right? All those bonds that are in those sigma bonds are as far away from each other as they possibly can get without running into whatever other groups might be on the other side, right? And so if 109.5 is the most optimal angle to keep these electrons away from each other, if we compress that angle to 60 degrees, we also get angle strain, right? Which is, again, lots of steric repulsion because you're forcing these two groups closer and closer together. So not only is there eclipsing interactions between these two groups here, there's also eclipsing interactions between literally carbon A and the bonds coming off of it from A to B and B to C. And so all of these bonds are just constrained into this very small space, which means that the electrons that are in those bonds are constrained and forced to kind of repel each other or forced into close proximity to each other. And so they start repelling each other. And so you end up with a huge amount of steric repulsion. So angle strain is one factor, right? Because it's less, the angle is less than 109.5, right? Because the angle is less than 109.5, we increase the steric repulsion. Because it's in an eclipsed conformation, because it's forced to be, we also have lots of steric repulsion there. So cyclopropane in general is a very unstable molecule. Very unstable, right? In fact, cyclopropane is basically rocket fuel, right? If you put any energy into cyclopropane, all of those electrons, right? If you put enough energy in, those electrons will just separate, and they'll do so very energetically. They will get rid of all that repulsion energy that they've been storing up, and so it's a huge amount of potential energy. That's why it's a good rocket fuel. So if you ever get any cyclopropane, you have to store it in a bunker underground and all that other fun stuff, right? Like all the good chemicals. Okay, so cyclopropane is one example. And cyclopropane is, of course, the worst of those examples. You can't have a two-membered ring. That's not a thing. So the smallest possible ring, cyclopropane, is the least stable. Cyclopropane is the least stable. And then as you get larger, right? So if we go to cyclobutane, you would imagine now the bond angles are going to get a little bit better. If you imagine a square, right, the angles are going to be 90 degrees. So the bond angles get a little bit better. You have a little bit more freedom to rotate, and so it's a little bit less bad than cyclopropane. You get to cyclopentane, if I could spell. If you get to cyclopentane, right, in cyclopentane, then you're starting to get to reasonably stable, right? Cyclobutane, I would still say, is kind of unstable. Cyclopentane was over to kind of stable. We could go a lot more in depth on these, but I really don't think that that's worth our time, right? And then we get to cyclohexane, and cyclohexane is perfect, perfectly stable. And I'm going to kind of skip over cyclobutane and cyclopentane because if we look at the two extremes, cyclopropane and cyclohexane, what we'll see is that in between it's basically the same idea. All right, so let's look at cyclohexane. We have a six-membered ring. We got two hydrogens on each carbon. So let's label this one carbon A and this one carbon B, and then we're going to draw a Newman projection. And I'm going to cheat a little bit because I know where this is going, but I'm going to put the 2 hydrogens on each carbon. So my 2 hydrogens on carbon A are here and here. My 2 hydrogens on carbon B are on the back one there. And then this is kind of the rest of the ring. So these 2 things are going to connect, right? So if we kept going, this would be carbon C, D, E, and F. So this is carbon C up here, and this is carbon F down here. And then the other carbons are in there. I don't really care about what they are. But notice that now we are in a staggered conformation, right? When we have a 6-membered ring, we can do a staggered conformation. Now, it's not anti, right? The 2 largest groups are, of course, carbon C and carbon F. They're much bigger than the hydrogens. And so we're still in a gauche conformation, right? We're in a gauche staggered conformation, which isn't perfect, but it is much better than eclipsed. Okay? And if we measure the bond angles of cyclohexane, the bond angles of the carbons in cyclohexane are 109.5 degrees, which is of course exactly what they want them to be, what we want them to be in for a tetrahedral carbon. And so we get this very nice relationship of 109.5, which is exactly what we want. All right, so this is why cyclohexane is very, very stable. We can get to a staggered Newman projection where the bonds don't overlap at all. So we minimize steric repulsion to a degree, right? We're still in a gauche conformation, but given that it's a ring, we can't really get out of that. We can't have the 2 parts of the ring going opposite each other and then still coming around to connect, unless we're talking about a very, very large ring, which has its other issues. So we're able to get into a staggered conformation, which is good. We have the right bond angles. 6-membered rings are great. They're very, very stable. Right, that's the takeaway message from all of this. In the next video, we'll look at what does that structure actually look like, and we'll look at how to draw chair conformations. So stick around for that.